Section 5.2, Applications of Integration Volumes. Calculus can be used to find volume as well. So here's a general solid in 3 space, a loaf of bread, not given by a handy formula for volume, like the volume of a right circular cylinder is pi r squared h, but we can determine the area of a cross section. So you cut this thing with a plane perpendicular to the x-axis, and you can see that there's a region in there and we have access to an area function a of x, which gives the area for any input x, area of the cross section. And so we do what we do, right? I mean, how do we get from area to volume? We are going to take that two-dimensional region and we're going to give it volume by extending it in the missing dimension delta x. And so now we've created a little cylinder. A slice is, each of these slices is like a little cylinder, not a right circular cylinder, but it is a cylinder, and it has area, it has volume, area of the base times the height, right? That's area of a box, area of a cylinder, area of anything is area of the base times the height. Not area of anything. A sphere you can't, use area of the base times the height. But for many solids you can. And so now if we add the volumes of all the slices, we can approach the volume of the entire solid. And of course that approximation will get better and better and better. We can start here with about 10 slices, and we can see that the sum of the volumes of those slices is going to approach the volume of the solid, the loaf of bread, and that approximation is going to get better as we increase the number of slices from 10 to say 20, and even better as we go from 10 to 30. Well, as the number of slices increases without bound, goes to infinity, we approach the actual volume of the solid. So here's a formula. The limit as n goes to infinity of the sum of, as k goes from 1 to n, of area at the kth slice delta x. So the products of area of the base times the height, the sum of those, and then let the number of those go to infinity, and now we've got the integral from a to b, a of x dx. And so here's a formula for general slicing method. It's not any particular kind of solid, but it is a general solid. A solid object extends from x equals a to x equals b. Cross section of the solid perpendicular to the x-axis has an area given by a function a. That's the hard part, usually, is trying to find that function a. A function a that is integrable on the closed interval ab. The volume of the solid is integral from a to b, a of x dx. And it just makes sense that that would be the case. We just saw why that was. So here's an example. Volume of a sphere of radius r. Show that it is the familiar formula 4/3 pi r cubed. Okay, so that is going to be the volume, regardless of where in 3 space we place this sphere. So let's place the sphere so that it centers at the origin. The plane P of x, okay, so there's a plane P of x, which is going to cut this sphere in a circle that has radius from the Pythagorean theorem, y equals the square root r squared minus x squared, right? Because a squared plus b squared equals c squared. The square of that length plus the square of that length equals the square of that length. X squared plus y squared equals r squared. We could solve for y squared, and then that would be r squared minus x squared, and then we could get y by taking the square root of that. And so that is an expression for y, and that will be what we need to in an integral to find the volume of the sphere. The cross-sectional area, the area of that purple circle, is pi y squared, right? Because area of a circle is pi r squared, okay? And the radius of the circle, not to be confused with the radius of the sphere, this radius of this circle right here is y, but of course we have an expression for y. Y is r squared minus, y squared is r squared minus x squared, right? Y squared is the square of the square root of r squared minus x squared. Y squared is r squared minus x squared. So area of a circle is pi r squared, and that's pi r squared for that purple circle. Pi r squared minus x squared. And so now we have area, and we're going to integrate from negative r to r this function with respect to x. So there's our area of the circular cross-section, pi r squared minus x squared. We're integrating from negative r to r because that's how our circle, that's how it sat along the x-axis. And so we're going to simplify this a little bit by just saying 0 to r because the integrand is even. That's an even function. Remember, r squared is being held. That's a constant right there. It's not a variable, even though it's a letter. We are integrating with respect to x. So this is just a second degree function with a constant in there. That pi we're going to pull out of the integral, and because it's even, of course, we're going to be able to double just the integral from 0 to r, and that'll be the same thing, and it'll simplify the computations for us. Well, now we are going to get an antiderivative, which, since r squared is a constant, its antiderivative is that itself times x, and the variable is x, so the antiderivative of x squared is x cubed over 3. And so we have an antiderivative which is going to be evaluated at r and at 0. Then we'll have the subtraction, whole thing multiplied by 2 pi. Substituting the r for x, we have r squared r, or r cubed, minus r cubed over 3. Well, 1 r cubed minus a third r cubed equals 2/3 r cubed. Right? 1 r cubed minus a third r cubed equals 2/3 r cubed, but multiply 2/3 r cubed by 2 pi and you have 4/3 r cubed. The familiar formula for the volume of the sphere of radius r. Okay, now let's talk about a particular kind of volume, and that is a volume of revolution. Okay, so we're going to take an area, we're going to revolve it around the x-axis in this case. So this is just some region R, it could be anything, and we're going to create a solid by revolving or rotating the thing around the x-axis. The entire region, it will sweep out region in 3 space. Okay, so we see the sweeping happening, and then a solid of revolution is generated. Okay, so here's how it looks, and the volume, of course, according to what we just learned, a general method of volume by slicing is integral a to b a of x dx. And a of x this time is the area of this blue circle. It's a circle, so its area is pi r squared. And so if we can get an expression for, if we can get the f of x there, that will be the radius of the circle. That's the thing that's going to be squared, the result multiplied by pi, the result of that integrated. Cross sections of a solid revolution are circular disks, as we give this circle volume by giving it width of dx. Circular disks of radius f of x and area pi times the square of f of x. So that's a pi r squared here because that cross section is a circle, and it's always going to be a circle in solids of revolution. And so a special case of the general method of slicing is the disk method about the x-axis. Let f be continuous with f of x greater than or equal to 0. So we're at or above the x-axis on the closed interval AB if the region R bounded by the graph of f, the x-axis, and the lines x equals a, and x equals b is revolved about the x-axis, the volume of the resulting solid revolution is. Now there's the formula that you have to know and memorize and use in this section. Integral from a to b, pi times the square of f of x dx. Okay, so here's a function, and we could take this region R, revolve it around the x-axis, and at x we're going to create a circle for the cross-section, and f of x then will be used in our volume of solid of revolution formula. And so we get this bugle as a result, okay? And, here's function f of x equals the square of x plus 1. And that's the height. That's also the radius. of the circular cross section. Area of a circle is pi r squared. So pi times the square of x plus 1. And so to find the volume of this bugle, we will need to integrate from 0 to 2. We're going to find the integral from 0 to 2 of this pi times the square of f of x. Okay, so we can simplify things by moving this constant outside of the integral. So pi 0 to 2, and we have the square of x plus 1. Well, if you have a to the m, whole thing to the n, it's a to the mn. If you have a power of a power, you multiply the powers. So this is actually the fourth power of x plus 1. The fourth power of x plus 1. And, well, we could do a u substitution. That would make things easy because its derivative of u is if u is x plus 1, then du is dx. Because that's just 1x right there. 1x to the first, so du is dx. Then we can rewrite this integral as the integral pi times the integral 0 to 2 u to the fourth du. And it can be directly written with the u variable in this way. Now, this is not exactly right, of course, because this is x equals 2. X equals 0 to x equals 2. But our variable here is u. So as when x is 0, u is 1. And when x is 2, u is 3. So this is actually pi times the integral from 1 to 3 of u to the fourth du. Simple power rule. Antiderivative is u to the fifth over 5. Integrating from 1 to 3. So pi will be multiplied by 3 to the fifth over 5 minus 1 to the fifth over 5, which is pi times 243 over 5 minus 1/5, which is pi 242 over 5, or 48.4 pi. 48.4 pi cubic whatevers is the volume of the bugle. Okay, so other regions can be revolved, and we can find the volumes of them. You might have a region between two curves, f of x and g of x, and you might want the volume of that region revolved. And so you can imagine how we would find that volume. Okay, with the revolution, we get not a circle for a cross section, but a washer is what we would call that blue thing. It looks like a compact disc, but it's called a washer, and so therefore to find it, the volume of the solid with the hole in it, it's called the washer method. That cross-sectional area is area of the big circle minus the area of the little circle, right? The blue area is pi r squared for the big radius minus pi r squared, little r this time, for the little circle in the middle. Pi, we can factor out pi, so r, big R squared minus little r squared, which is, well, what this is here. Okay, that's the cross-sectional area, and that's our a of x for integral a to b a of x dx. Okay, so washer method, same conditions. We're going to say f of x greater than or equal to g of x on this closed interval AB, and we're going to make them both positive. As we saw in the picture, continuous functions. And so the volume of the solid generated by revolution for that region is integral a to b pi times the difference of the squares of the functions dx. Washer method. Okay, the cross sections are washers, not circles. We can also find a volume for a solid revolved not around the x-axis but around some other horizontal line. We can also find a volume for a solid rotated about the y-axis, and that's going to go similarly. We're going to integrate from c to d, where c is less than or equal to d. Of course, if c is equal to d, then that integral will have a value of 0, and you won't have any volume at all. But pi times the square of r of y, so we're going to think of x as a function of y, r of y, dy. That's what we would use here to find the volume of this rotated region in the xy plane. Okay, this region here, we're going to rotate it about the y-axis, and so we would use that formula, integral c to d, which in this case would be 1 to 4, integral c to d pi times the square of r of y dy. Now we see how x is a function of y, so the r of y in this case would be 2 over y. And there's also a washer method for solids of revolution about the y-axis.